in this tutorial, we are going to discuss the problems related to the optical sources. We have seen while discussing theory that there are two types of sources which are used for optical communication. One is LED, the light emitting diode, and other one is ILD, which is the injection laser diode. We have seen the operation of LED, the basic principles behind the emission of light from LEDs. We also saw the principle related to the lasers. So, in this session, we are going to solve some problems related to LEDs and the laser diodes. So, let us look at the first problem here. This problem is essentially related to designing a material for emission of light at certain wavelength. We have seen while discussing LEDs that there are these ternary materials which when combined in right proportion they form an alloy, and the band gap of the material can be manipulated by changing the mole fraction of the ternary materials. So, here is an example where we are having a ternary material which is gallium aluminum arsenide. The problem says that this material gallium 1 minus X, aluminum X, arsenic emits a wavelength of 0.7 micrometer. Find the aluminum mole fraction X if the band gap energy for the material is given as, and that is band gap energy is given as 1.424 plus 1.266 x plus 0.266 x square. So, this problem is a very simple problem. So, essentially what we are going to do, first we convert the wavelength of emission to the corresponding band gap energy. So, it is given that lambda for the LED is 0.7 micrometer. We know from the very basic relation that the band energy is given as 1.24 divided by the wavelength of emission in micrometers. This band gap energy is given in terms of electron volts. So, if you substitute 0.7 in this, we get the band gap energy which is 1.24 divided by 0.7, that is equal to 1.77 electron volts. Once we get the band gap energy, then the problem is very simple. We substitute this in the expression which is given there, and then we find out the corresponding value of x. So, that becomes a simple algebra. So, then we have here 1.77, that is Eg, that is equal to 1.424 plus 1.266 x plus 0.266 x square. By rearranging, we get a quadratic in terms of x square. So, that gives us 0.266 x square plus 1.266 x. Bringing this term on this side, you get minus 0.346, that is equal to 0. By solving this quadratic, you will get the value of x, and that is equal to 0.259. So, this is one of the most simplest problem, which says that if you are having a material gallium 1 minus X, aluminum X and arsenic, then for this value of X, which is 0.259, this ternary material will emit a wavelength which will be 0.7 micrometer. So, this essentially says that whenever we try to design the LEDs corresponding to different wavelengths, you have to find out a proper combination of these materials, and by manipulating this mole fraction of the constituent elements of this composite material, one can design a material to find out the wavelength of emission, and which can be tailor made depending upon the requirement. So, this is one of the very simple problems related to the LED. Let us consider the second problem. Now, this problem is related to finding out the radiative recombination lifetime of a semiconducting material. So, if you get an LED and if you inject current inside the LED, then the recombination takes place, and depending upon the recombination rate, the speed at which the LEDs can be modulated, that is decided. So, here the problem is an LED has a 50 micrometer diameter emitting area and operates at a peak modulation current of 100 milliamperes. It is also given that this current falls in the domain of what is called the high injection. Find the bandwidth of LED having 2 micrometer active area thickness. The recombination constant Br is given as 10 to the power minus 10 centimeter minus 3 per second. So, let us start with the basics of finding out the recombination equation. So, let us say we are having inside the LED the delta n carriers are injected, and let us say that equal number of holes are injected. So, delta n is equal to delta p. So, now the rate of recombination or decrease in the injected carrier per unit time, that is given as the recombination constant Br times the product of the electron density and the hole density. So, this is n 0 plus delta n times p 0 plus delta p. These are the carrier which are injected inside the junction. However, there are going to be thermal generation which you have to take care of. So, you subtract the thermal generation which is Br into n 0 into p 0. Now, we can do little algebra here which gives that minus d by delta n by delta t, that will be equal to the recombination constant Br times this n 0 p 0, this term will cancel with this. So, you get here n 0 plus p 0 delta n plus delta n into delta p, and if assuming delta n is equal to delta p, this is delta n square. So, from here now if you take the high injection, the delta n is much larger compared to this quantity. So, we get for high injection delta n is n 0 or p 0, and then you get the rate of decrease of the injected carriers, that is equal to Br to delta n square. We can write that as Br delta n to delta n. So, then the radiative recombination lifetime essentially is 1 upon this quantity. This is simple first order differential equation which gives that the carriers, injected carriers are exponentially decay with a lifetime which is 1 over this quantity. So, you get here then the tau r r, that is equal to 1 upon Br into delta n. But we also know that this delta n, if you consider a junction, then that is the region where the carriers are injected, which is the active region, and that is the area and that is the depth. So, in this volume essentially you are going to have the excess carriers. So, the injected carrier density delta n, that is equal to the injected current I divided by the charge of the carrier Q divided by the volume of this region, that is the area of cross section, and the d. So, you have a area of cross section here, that is A, the thickness of the active region is d, and the lifetimes are going to remain there. The carriers are going to remain there for the lifetime, which is tau r r. So, this delta n will be given by this. So, if I take this delta n and substitute into this, I will get a term which is tau r r square. So, by substituting this, then we can get tau r r, that is equal to square root of q a d divided by the recombination constant B r to I. Now, all these quantities are given here. The q is the electronic charge which is given. So, q is 1.6 10 to the power minus 19 coulomb. The area of LED junction is given because it says that the LED has an emitting area of 50 micron diameter. So, A is given as pi 50 into 10 to the power minus 6 micron square divided by 4. D, which is the thickness of the active region, is given as 2 into 10 to the power 6 meters. This is meter square. And B r is a quantity which is given recombination constant, that is 10 to the power minus 3 minus 10 centimeter minus 3 per second. So, this will be equal to 10 to the power minus 10 into 10 to the power 6 meter minus 3 per second. So, now we know all the quantities in this expression. We know q, we know the area of cross section, we know the diameter, we know the thickness of the active region, we know the recombination constant. So, from here then we can calculate this value of tau r r. So, tau r r can be calculated. Once you know tau r r, then the bandwidth of this device delta omega is approximately 1 upon tau r. So, substituting these values of A, D, B, R, Q, we can calculate this value of tau r r, and taking 1 upon that, then we can find out the approximate bandwidth which the LED will have. So, one can do simple calculations to get the bandwidth corresponding to the LED. The third problem is related to the injection laser diode. It says that when you are having, if you write the rate equation for the injection of the carriers inside the junction, then there are two processes which are going to take place. One is the injected carrier, which are the excess carrier which are going to be in the region. These carriers are going to exponentially decay as the time goes with the recombination lifetime, and then the net change in the carrier density in the region is the balance between these two. So, this problem essentially is the equation giving the balance between the injected carrier and the recombination of the carriers. So, the problem is when a current pulse IP is applied to an unbiased laser diode. Unbiased means that when the current is not applied, when the pulse is not applied, the current injected inside the laser diode is 0. So, pulse IP is applied to an unbiased laser diode. The injected carrier density delta n in the recombination region changes as, then the equation is given here, which is d by dt of delta n is equal to IP divided by QAD, where Q is the charge, electronic charge, A is the area of cross section, D is the depth of the active region. So, this is the excess carriers which are injected inside the junction, minus the recombination of the carriers which are having a lifetime of tau. So, minus delta n divided by tau. So, that is the equation which governs the carrier density inside the active region. So, it is asked that if the laser threshold current is I threshold, show that the time needed for the onset of the stimulated emission is by the expression which is tau d equal to tau ln IP divided by IP minus I threshold. So, this problem also is essentially related to solving the differential equation which governs the excess carriers in the recombination region. So, here we get d delta n by dt, that is equal to the injected current which is IP divided by the electronic charge, area of cross section, d is the thickness of the active region, minus delta n divided by the carrier recombination lifetime tau. Now, this equation can be solved very simply. So, the solution of this equation we know as a function of time, n is as a function of time, can be given as IP tau divided by Q A d into 1 minus e to the power minus t divided by tau. One can verify that when t is equal to 0, that time the injected carriers are 0, and when t goes very high, then essentially you reach to a steady state, and that is the carrier density you are going to have in the steady state domain. So, it is the carriers, number of carriers per unit time multiplied by the recombination lifetime. So, that is the steady state density you will see inside the junction of the laser diode. Now, it is said that, so that if you look at the laser characteristic, we know that if the laser was unbiased, the initial current is 0, and then for lasing to take place, the electron density has to increase to a certain value where population inversion takes place, and then the laser will start lasing. So, it is going to take certain time to build the electron density in the recombination region to a minimum required value. So, let us say that time which it takes to build that electron density is given by T d. So, then we have at T is equal to T d, that much delay is there in building that electron density, the current reaches to the threshold current. So, if I take this and substitute into that, you will see that the delta n threshold, if you calculate, that will correspond to the I threshold tau divided by Q to A d. So, after T equal to T d, then the threshold, the current should reach to threshold current, that means the carrier density should reach to this value. Now, the problem is very simple, you can take this and substitute into this equation. So, you get I threshold tau divided by Q A d, that is equal to I p tau q a d into 1 minus e to the power minus t d divided by tau. This term will cancel, the tau will cancel, the q a d will cancel, and we will get a simple expression in terms of I p, I threshold, and the lifetime of the carriers tau. So, e to the power minus t d by tau, that is equal to I p minus I threshold divided by I p. Just inverting this, then we get the delay, which is t d, that is equal to tau ln, taking log on both sides, I p divided by I p minus I threshold. That is what actually we wanted to show, that the delay which is going to take place in this, in building the population inversion up to the threshold value, that actually is given by this. This relation is the important relation, because what it tells you is that if the laser was biased at 0 current, then it will require certain time to build the population inversion. So, if you wanted to modulate it at a faster rate, you will not be able to laser it at a very faster rate, because this much time is required to get the laser into action. So, this parameter essentially tells you about the speed of the device or modulation speed which the laser would have. So, of course, if the threshold current was equal to was large, then this quantity will become smaller and smaller, and then you will see that the speed increases, but this quantity essentially goes down. So, whenever we want to operate laser, we must make sure that the laser is biased at the threshold current. But this problem essentially tells you that if it was not biased properly, then it requires certain time to get into action, because the laser has to build the population inversion, and that will require certain time. So, this is a simple problem which is related to the basic operation of laser diode. Let us look at now a problem related to the helium neon laser. We all know the helium neon laser is used in pointers in laboratory experiments, because that is the laser which gives the red light. The optical communication uses optical spectrum which is in infrared, but in laboratory when we conduct experiments, we want to have a light which is visible, and helium neon gives a wavelength which is 632.8 nanometer, which is a red color. So, this is the laser which is very commonly used. So, the problem here is that if the half width of helium neon laser, which corresponds to a transition of 632.8 nanometer, and the bandwidth of this transition is 1500 megahertz, what must be the length of the laser cavity to ensure only one longitudinal mode oscillation? Estimate the accuracy to which the temperature be maintained if the frequency stability is to be better than 10 to the power 8 hertz. Take coefficient of expansion of the laser tube to be 10 to the power minus 6 per degree centigrade. So, as we know that in the lasers, we are having this transition energy levels, and the electron makes a transition from here to here, and that gives you a laser light, is the stimulated emission. We also know that because of various factors, these energy levels are not really sharp. So, these energy levels are little diffused, and because of that you do not get a monochromatic light from the laser, but you get a certain bandwidth associated with the emission from the system. So, what is given here, that you are having a spectrum of a laser which is like this, and the center wavelength of this is 632.8 nanometer, which is the red color. It is also given that the half width of the spectrum, emission spectrum, is 1500 megahertz. So, now if you want to have only one mode, essentially what we are saying is that the line separation for the mode which are generated inside the cavity of this laser should be more than this, or should be at least equal to this. If you make sure, then only one longitudinal mode will propagate inside the cavity, and then you will get only single mode output from this laser. So, now write the simple relation that the mode number m inside the laser, that is equal to length of the cavity divided by lambda by 2, and if the medium is not air, then you are having a refractive index for that medium, which is given as n. Now, for helium neon laser, since the medium is a gaseous medium, the n can be taken approximately equal to 1. So, take n approximately equal to 1. So, that simply says this is equal to 2 L divided by lambda. Now, we find out what is the, if we consider the adjacent modes, then we want to find out what is the change in the wavelength, or what is the spacing between two adjacent modes in terms of the wavelength. So, we can differentiate this to get d m is equal to minus 2 L upon lambda square into delta lambda. But in this case, we are not given the spectral bridge in terms of the wavelength. We are given now the spectral bridge in terms of the frequency, 1500 megahertz. So, rather than using this relation in terms of lambda, let us use this relation in terms of frequency. So, this will be 2 L divided by lambda, we can put as C into the frequency, or if I differentiate now with respect to frequency, that will be equal to 2 L divided by C into d f or delta f. Now, for the adjacent mode, the d m is equal to 1. So, for adjacent modes, d m is equal to 1. So, from here we can find out what should be the value of L, so that I get the lines which are separated more than 1500 megahertz. So, if I substitute d f equal to 1500 megahertz, I can find out value of L, and that is for d m equal to 1. So, you will get from here L, which is C divided by 2 d f, which is equal to 3 into 10 to the power 8, the velocity of light, 2 into the transition bandwidth, which is 1500 multiplied by 10 to the power 6 for megahertz, and meters. So, if I solve this, you will get a length of this is 100 millimeter. So, this tells us that if you take a helium neon laser tube, which is about 100 millimeters, then it will generate a single mode propagation if the transition bandwidth is about 1500 megahertz. So, that is the first part of the problem. What should be the length of the tube to get a single mode longitudinal oscillation inside the cavity? The second problem is that if you wanted to have a certain stability for the frequency emitted by the laser, then the length of the tube should not change, but as a function of temperature, because the expansion coefficient, the size of the tube is going to change, and when the size of tube changes, the resonant frequency changes, and because of that the frequency of the laser changes. So, now the question we are asking is how accurate the temperature should be maintained, so that we do not have a deviation in the frequency more than 10 to the power 8 hertz. So, again we can go back to the same relation to find the stability of the frequency. So, using the same relation here, we can write that the frequency is given as C m divided by 2 L. So, we can ask the deviation in frequency now as a function of L. So, if I ask delta f how much is going to be because of change in the length, this will be minus C m divided by 2 L square multiplied by delta L. But this quantity again can be substituted for the center wavelength of the laser. So, this gives delta f divided by the center wavelength of the laser f naught, which is equal to delta L divided by L. And center wavelength or center frequency of the laser f naught can be calculated, because we know the wavelength of helium neon laser. So, it is 3 into 10 to the power 8 velocity of light divided by the wavelength of helium neon, which is 632.8 nanometer 10 to the power minus 9. And we are given that now the stability has to be better than 10 to the power 8 hertz. That means, this quantity delta f for this problem is 10 to the power 8 hertz, is also hertz. So, if we substitute into this, we get delta L upon L, which is equal to 10 to the power 8 divided by this quantity f naught, which will turn out to be 0.21 into 10 to the power minus 6. Now, the length expansion coefficient is given as 10 to the power minus 6. If you substitute that, then we can get a temperature accuracy equal to 0.21 degrees centigrade, because the expansion coefficient is given as 10 to the power minus 6 per degree centigrade. So, this calculation show that if you make a helium neon laser and if you wanted to have a single mode operation for the kind of parameter which are given, then the tube length has to be 100 millimeters, which is about 10 centimeters, and then this length has to be maintained for this accuracy of 10 to the power 8 hertz. So, the temperature of this laser has to be maintained with an accuracy better than about 0.2 degrees centigrade, then the frequency stability of 10 to the power 8 can be achieved. Let us now look at a problem which is related to the semiconductor lasers. We have seen from the radiative equation of the laser that when the current is injected inside the laser, it requires certain time for building the population inversion, and then only the laser gets into the lasing action. So, we know that when the laser, if the speed of the laser has to be increased, then the laser has to be biased at the threshold current. Now, if it is not biased at the threshold current, then from the biasing point the time is required to get into the up to threshold current, and beyond that then the lasing action essentially starts. There are many reasons why the laser cannot be exactly biased at the threshold current. So, the bias current normally is different than the threshold current, it may be little smaller than the threshold current, and in that situation we have seen that the delay for getting the laser into lasing action is given as T d, which is equal to the lifetime of the carrier ln, the peak current which is injected inside the laser divided by I p plus I b minus I threshold, where this is the peak current which is injected, this is the biasing current, and that is the laser threshold current. Now, tau is the lifetime of the carrier, and this is to be calculated from the data which is given inside this in the problem. So, now the problem is the semiconductor laser has a threshold gain of 50 per centimeter, and the semiconductor has a refractive index of 4. The threshold current for the laser is 100 milliamperes, and the laser is biased at 50 milliamperes. The laser is to be modulated by the current pulses of 150 milliamperes. What is the highest pulse rate to which the laser can be modulated satisfactorily? So, as we have seen in the earlier problem, the speed can be calculated if I know this time, which is T d. All these parameters are given, I p is given, I b is given, I threshold is given. Only this is a quantity which is not given directly in this problem. What is given, however, is what is the threshold gain, which is G T h, that is threshold gain. So, essentially a photon remains inside the cavity for 1 over this quantity, that is approximately the distance which the photon travels inside the cavity. So, if I want to calculate what is the lifetime inside the cavity, this tau, so this tau will be equal to 1 upon G threshold. This is the on average distance travelled by the photon before it decays, divided by the velocity of light in the medium, which is c divided by n, where n is the refractive index of the material. Now, G T h is given, n is given for this problem. So, this is n divided by c to G T h. We can substitute the parameters given in this problem. The refractive index n is 4, the G T h is given as 50 per centimeter, c is the velocity of light. So, we substitute these quantities in the expression. So, we get 4 divided by 3 into 10 to the power 8 meters per second multiplied by 50, this is given in per centimeter. So, 10 to the power 2. So, if you just solve this, we get the tau, which is 2.66 picosecond. So, tau d, which is the delay, is given as 2.66 ln I p is given as 150 milliamperes. So, this is 150 plus the bias current is given as 50 milliamperes and the threshold current of the laser is 100 milliamperes. So, that is equal to 2.66 ln 150 divided by 100 that is equal to 1.07 picosecond. So, the pulse rate, maximum pulse rate which the laser can be modulated to maximum, that is approximately 1 upon T d. So, that is equal to 1 upon 1.07 into 10 to the power minus 12 for picosecond. So, that will be equal to 943 gigahertz. So, this problem essentially is a problem related to when the lasers are biased, how the laser should be biased, and depending upon the biasing point, what kind of modulation rates can be achieved from the laser. Okay. Let us look at another problem related to the laser. A material having refractive index of 4.5 at 1300 nanometer is used for making a laser cavity 400 micrometer long. The refractive index varies linearly as a function of wavelength at a rate of 10 to the power minus 3 per nanometer around 1300 nanometer wavelength. Find the separation between the cavity modes. So, we have seen the relation for finding out the separation between the lines inside the cavity, but in those problems we have assumed that the refractive index of the medium remains constant as a function of wavelength. Here we are saying now that the material used for creating the laser, that material is a dispersive material because the refractive index is varying as a function of wavelength. So, in this situation we are asked to find out what should be the line separation for the cavity modes. So, again we can start with the basic relation that the length of the cavity required is the mode number lambda m lambda divided by 2n. Same relation which we have used earlier in earlier problems. So, again from here we can get m equal to 2n L divided by lambda. Note here however, in this case now the n is a function of wavelength, it is not a constant quantity. So, as we have done earlier, to find out the separation between the modes, if I differentiate this with respect to lambda, you will get the change in m, which is the modal index, that is equal to 2L. I can differentiate this quantity with respect to lambda. So, that is lambda T n by d lambda minus n divided by lambda square multiplied by d lambda. Again for the adjacent mode, this quantity d m is equal to 1. So, this quantity we put equal to 1 for the adjacent modes, and then inverting the relation, then one can get d lambda which is equal to lambda square divided by 2L, this negative sign here. So, there is n minus lambda d n by d lambda. Now, we are given all the parameters in this problem. The n is the refractive index of the material. So, that is given, n is given as 4.5. The rate of change of refractive index as a function of wavelength is also given. So, this quantity dn by d lambda is equal to 10 to the power minus 3 per nanometer. The L, which is the length of the cavity, is given as 400 micrometer. So, all the parameters are known now. So, we can find out what is the corresponding quantity, which is delta lambda, which is the separation between the two adjacent modes. So, if you substitute into this, you get d lambda, that is lambda is 1300 nanometer. So, this is 1300 square divided by 2 into 400 micrometers. If you want to convert into nanometer, 10 to the power 3 into 4.5 minus lambda, which is 1300, multiplied by dn by d lambda, which is 10 to the power minus 3. So, if you solve this, you get the separation between the lines for this laser, that will be equal to 0.66 nanometer. And that's what happens very typically for the semiconductor lasers, that the material refractive index is not independent of frequency or wavelength. So, this problem essentially is the problem related to if the material was dispersive, then one can find out what is the precise separation between the modes inside the laser cavity. Let us look at one more problem related to semiconductor laser. As we know, inside the laser, the gain function is a frequency dependent function, but the losses which take place inside the cavity, normally they are frequency independent. And as we know, inside the cavity, the two mechanisms operate simultaneously. The photons are generated because of the gain function, and the photons are lost because of the other loss mechanism inside the cavity. It is the net gain between these two which decides whether the mode will go into the oscillation or the frequency will go into the oscillation or not. So, if the gain is dominant, then that frequency has a tendency to go into oscillation. If the gain was less than the losses, then that frequency dies down exponentially. So, essentially those frequencies over which the gain is more than the losses inside the cavity, there is a tendency for amplification or going into stimulated emission. That is the thing which is captured into this problem. So, the problem is a gallium arsenide laser has a 400 micrometer long cavity with a refractive index of 3.6. The material gain function is Gaussian with its peak at 800 nanometer, and its sigma of the Gaussian function is 2 nanometer. The maximum gain at 800 nanometer is 50 per centimeter. If the loss in the cavity is 30 per centimeter and is independent of the wavelength, find the number of modes which will exist in the laser. So, let us first see what is given here. It is given that the gain function of a laser is a Gaussian function. The center wavelength for this Gaussian function is 800 nanometer. The peak gain which the function has is 50 centimeter minus 1. So, the Gaussian function, since the sigma is given as 2 nanometer, we can write this gain function G as 50 e to the power minus lambda minus 800, which is the center wavelength, square divided by 2 sigma square, sigma is given as 2, which is square. Then we are having a loss function which is independent of the wavelength, and that is this, which is 30 centimeter minus 1. So, that means over this wavelength range we have a gain more than the losses. That means, these are the frequencies which lie between this band from here to here. They have a gain, net gain into the system. So, these are the frequency which will go into oscillation. So, let us say this is the B, this is the thing which is the bandwidth over which we are going to get the gain into the system, net gain into the system. So, we can ask what is this wavelength here? Let us say this wavelength is lambda 1, at which the gain equals the loss. So, substituting the G equal to 30, we can get 30 e to the power minus lambda 1, because that is the wavelength at which the gain becomes 30 minus 800 whole square divided by 2 square. By solving for lambda 1 from here, we get lambda 1 is equal to 802 nanometer. So, this quantity bandwidth, which is 802 minus 800, which is 2 nanometer here and 2 nanometer here. So, the bandwidth which we have where the gain takes place is equal to 2 times 802 minus 800, which is equal to 4 nanometers. We want to find out what are the total number of modes now which are going to get excited in this bandwidth. So, again the exercise is very similar. We have to find out now what is the mode separation in terms of wavelength, and if we get that, then we can find out what is the total number of modes in this bandwidth. So, again we use the same relation that L is equal to m lambda divided by 2 n, and from here we can calculate delta lambda, which is lambda square divided by 2 L into n. This is the line separation. So, we can substitute the parameters. This is 800 nanometer laser. The length of the cavity is given as 400 micrometer. So, this is 10 to the power 3 into 3.6. So, we get delta lambda, which is equal to 0.22 nanometer. So, the total number of lines which will exist inside this laser corresponding to this bandwidth, which is 4 nanometer. So, we get number of lines equal to the bandwidth, which is 4 nanometer, divided by the line separation, which is 0.22, which is approximately equal to 18. So, in this tutorial, essentially we saw the problem related to the sources which are used for optical communication. There are some problem which we have seen regarding LEDs, finding out the bandwidth of the LED, finding the bandwidth of the laser, finding out the switching time of the laser depending upon the biasing of the laser, also the number of lines which exist inside a typical laser. So, normally whenever you use this component into practice, this information normally is required, because that tells you approximately what is the effective spectral width of your source. This problem also show that whenever we talk about laser, even the lasers, normal lasers do not have one mode propagating inside them. There are a large number of modes which propagate, and the effective width, spectral width of the laser is therefore typically of the order of about few nanometers. As you have seen in the lectures, to improve this, then there are other lasers which are used, which are the DFB lasers and so on. But this problem which we have solved in this essentially are for the typical lasers which are used for optical communication. So, this tutorial has given some hand on experience on solving the problems related to the lasers and the light emitting diodes.